So today we're going to begin talking about something called projectile motion, motion in two dimensions. We're going to see what happens when you launch something at an angle, as we have with this cannon right here trying to hit this target. We have an initial speed of 18 and an angle of about 29 degrees, and if we hit fire we can see that the cannonball makes that arc. Now, if we keep the angle the same but raise the speed at which it comes out of the cannon, you can imagine that it's going to go farther, which it does. Or we can go back to the original speed and change the angle. We can actually make this thing go at a steeper angle, see where it ends up. And we can see that you can actually approximately get to the same distance with a different speed or a different original angle. And so, but sometimes the cannonball is in the air a long time, sometimes it's in a short time, sometimes it goes farther, sometimes it goes not as far. And all of these different factors are dependent upon a couple of things. They're dependent upon the angle at which you shoot it out and also the initial speed. So if we, here's a different example. Ooh, we need to reset that. Here's our monkey cannon. We're going to shoot a monkey. That's right. Oh, that's going to leave a mark. So whenever we do this, let's try to make it so that we miss it. If we go, let's do snapshots. One of the things that we can do here is we can have it draw vectors for us to kind of trace the arc of the path that our cannonball takes. You can see that the cannonball is going to leave at an angle of 24 degrees and have a relatively large velocity. Let's just hit fire and see what happens. No, that was not nearly enough velocity. We need a little bit more velocity. Let's try this again. Oh, we hit the monkey again. But what that did was it left a little path, a little trace of vectors that, as we had talked about in class before, vectors are, you have horizontal vectors that describe how the thing is moving horizontally, and you have vertical vectors that describe how it moves vertically, and those are independent of one another. And so you'll notice that the horizontal vectors here are always exactly the same, because in the horizontal, other than air resistance, which we generally ignore in high school physics, it will be completely unaffected. There'll be no acceleration in the x direction. However, how it's moving up and down does change, and that's what gives us this parabolic arc. You can see that this vector gets a little shorter in the vertical, shorter, and then it becomes negative after the apex and begins to get bigger as you go down. And so, if you pause the video and look at that, or just Google, monkey cannon Oregon, you'll probably get there. So let's talk about how one goes about working out kinds of problems that you might be asked about here. And in order to do that, let's talk about a few basic terms. We have hang time. That's the time it takes for it to go to the top and then back to the ground. And then you have range, which is how far it goes in the horizontal. And then, of course, you can talk about how high it goes. Or you could also ask questions like just how long does it take to reach its apex at the top, or anything like that. And so we're actually going to do a fairly complex problem here at the beginning that if you can do this, you can do most of the others, involving not just shooting something off of a flat surface like this, but actually shooting it off of a tall cliff. So that's where we're going to begin. Ball is thrown from a 100-meter tall cliff at a velocity of 43 meters per second and an angle of 37 degrees above the horizontal. We're going to go through a series of different questions here about this scenario and try to answer them. We'll do our best. We'll give it the old college try. So, here's our 100-meter tall cliff. Here's the base of the cliff, and here is the alligator. That's an alligator. And so now we're going to put some thing at the top that we're going to throw off of it, and we'll just do this for a ball. Just throw a ball. So we're going to throw a ball, assuming the ball leaves approximately at the level of the height of the cliff, which probably isn't true, but we're going to ignore any difference between the person's hand height and the base of the cliff height. So we're just going to approximate this by saying that the ball was going to be launched from here, and it's going to head off at an angle of, well, that's not a very good angle here. Let's try that again. 37 degrees to the horizontal. So this is our horizontal. So this is 37 degrees. And so this is a vector problem. The 43 is how fast it's thrown at the very beginning. The 37 is the direction that it's thrown in the very beginning. And so, just like with the cannons that we just saw a moment ago, we're going to have a situation where it is going, it's going to be having both a vertical component as it's thrown and also a horizontal component as it's thrown. And so those vertical and horizontal components, it's like with all vectors, are going to be just represented as little arrows. And so my green vector here was going to represent the horizontal portion of the velocity, which we call Vx. And I'm going to make a blue arrow, which is going to represent the vertical, which represents Vy. Now there's nothing new about any of this. We all know how to find out the x and the y components. We're just going to use our basic trig functions. We're going to say that the v sub x over 43 is going to be equal to the cosine of 37 times 43. Oh wait, I just threw way too much in there, didn't I? Is equal to the cosine of 37. So 43 times the cosine of 47 is going to give us v sub x. So somebody have that number on a calculator. 34.3 meters per second. Maybe one too many sig figs, but that's all right for now. So we got our Vx is 34.3, and that is the answer to this question. What is the initial horizontal velocity? And by the way, if it then asks, what is the horizontal velocity when the thing hits the ground? If it asks, what's its horizontal velocity when it hits the ground, what would you say? You would say 34.3, because in the horizontal, the velocity isn't changing. That's the whole point, is that the velocity in the horizontal is constant. So all of our formulas involving horizontal, if it asks us for the how far it goes or anything like that, we don't need any accelerations, because there are no accelerations because it's constant velocity. And so we'll come back to that in a little bit. So the next slide then, if I can edit and copy and paste. The next slide is asking exactly the same question, except it's asking for the vertical initial velocity. The vertical initial velocity is that Vy number, so we're going to get it exactly the same way. We're going to take the sine of 37 is equal to the y component over 43. So 43 times the sine of 37 is the initial vertical velocity, which is what? 26. Oh, okay. Well, that's easy enough. Nothing too terribly difficult here. Now, unlike the x velocity, though, we have to realize that this number is only true at the moment that it's thrown, right here. That's the only time its velocity is 26, because, you know, it's just like when you launch something straight up in the air, it's going to go slower and slower and slower, and then it's going to stop, and then it's going to come back down, 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 down. So this number, anything that we ask about in the vertical, we are going to have to use an acceleration of negative 9.8 meters per second squared, because it's not going to continue. We all know that this is not going to continue going 26 meters per second forever. So that brings us to the next question, which is how high above the ground is the ball when it stops going up? So that turns out to be the kind of problem we've actually worked before. Question: is the x velocity going to have any impact on how high it goes? No. The x velocity doesn't. The x velocity is not going to impact how high it goes. It's the y velocity that impacts how high it goes. And we just found that the y velocity was 26, right? But that was an initial y velocity. For the x velocity, for the horizontals, we don't need any initial and final. For the y's, we do. We do need final, initial, and final for the y's. So, if we're asking how high it goes, so let's kind of trace out this arc. Woo! We're really asking if it starts here, we want to know how long it takes to get to that point. And we know that it's y velocity at that point. What is its y velocity? This is all a y picture. We don't care about the x at the moment. What is the final y velocity at this point? It's 0, because it's at the apex. We did problems like this before, but in the before, we were throwing things straight up and straight down. Now it happens to be moving across as it's going straight up and straight down, but it changes nothing about the up and down portion of it. The two are independent of one another. So now we have the, how are we going to do this then? If we know the initial and we know the final and we know the acceleration, we can find that time, can't we? The time is going to be, so 0 equals 26 plus negative 9.8 times the time. So 26 over 9.8 is going to get us the time. So how long does it take to go from here to here then? How long is that? Let's just call it 2.7 seconds. And so that is the answer to slide C. How far above the ground is the ball when it stops going? Oh, no, it's not. That's not the answer. It's asking how high it is. I guess we answered the wrong question, but if we had been asked that, we could do that. So what we need to do is, if we want to know how high it is, what we need to do is figure out this distance. And so that's going to be, I believe we have enough information to do that as well. Vf squared equals Vi squared plus 2AD. So the final, again, is 0 squared equals, the initial is 26 squared equals, or plus, keep doing that, plus 2 times 9.8 is 19.6 D. So 26 squared divided by 19.6 is what? $34.5 meters. So 34.5 meters. So this goes up 34.5 meters. Is that the answer to the question as stated? Got to be careful. Is that the question as answer the question as stated? No, that's how high it is above the cliff. And you got to add, as he said, you got to add 100, because that's how high it is above here. So that's 34.5, and that's 100. So the answer is 134.5 meters above the ground. Okay, so the next question is going to take more than 50 seconds. I'm going to have to hit stop here and let it process this video before we move on to the next video. So, because I'm too cheap to pay for the pay version. I think it's like $10, maybe $15. I'm not going to pay that. Because on the paid version, you can go for like as long as you want, but here you're limited to 15 minutes. Sorry, Heather.